Hello everyone, this is John Buck back with another continuous time linear systems video. And this video is another example of block diagrams in Laplace, where I'm going to go from the block diagram to get to h of s and eventually the differential equation. So this assumes you've already seen the basic video on block diagrams in Laplace. If you haven't, you should pause this one and go back and see that general background so that you can see this example to go with it. But again, if I look at this, I'm going to be working, I may have my input and output labeled in the time domain, but I'm going to be working with things in terms of the Laplace transforms. And actually, let me try to keep the colors the same as the example I just did. So we're going to do things related to the Laplace transform of the input in green, even though the whole block diagram is just drawn in one color. And I'll have y of s for the feedback terms. And what I'll do now is I'll just think about this x of s flowing through the system. I could go at it a couple ways. I could take the output and work its way back, or x working its way forward. But so, for example, if this branch here is x of s coming in, this thing here will be 3x of s. And I usually just go through labeling the different nodes, whereas this one will multiply by 1 over s, right? We know that's actually an integrator in the time domain, so I get 1 over s, x of s. And then it gets scaled by a minus 5. So I get minus 5 over s. Try to make sure my s's look clearly different from my 5's. So minus 5 over x of s. And if I now look in the output branch, maybe I've got an adder here, but I don't know what this other thing is. I don't know what this thing is. So I need to come back here and follow my output for a bit till I can fill in more of the branches on this side. So I get a 1 over s, y of s here. And I didn't leave myself enough room here to label this one, but it would be minus 2 over s times y of s. And now I've got both inputs here. I've got both branches coming into the input, minus 5 over s, x of s, minus 2 over s, x of s. So this branch up here, I'm going to just sort of bring this line down, would be minus 5 over s times x of s, minus 2 over, and this part should be blue, minus 2 over s times y of s. I'm going to clean the other one up too. And now I'm just about done in terms of what I need to find the output from the input, and that I've got this branch and this branch to the output of the adder. This output is y of s, but we know now it's also the same as the sum of these two input branches. So this branch here is also, let me sort of use white as my little probe here. So saying if I look at that branch there, I shouldn't put circles on it. That's bad notation. So just if I look at that branch, I would have 3x of s from the one input. And then the other input would give me minus 5 over s, x of s, and then minus 2 over s, y of s. Right, so, and this is equal to y of s, because that's just what's flowing out. So sort of by solving it each way, I sort of almost feels kind of magical. I've gotten to my answer that y of s for the system is also equal to this branch here. So I'll get minus, I'm going to reorder the terms to keep the y's a little closer together, minus 2y of s minus 5 over s, x of s, plus 3x of s. Okay, so I'm almost done here. I've got my whole input and output in terms of each other. I just need to pull all the y's and x's together, and I can solve for h of t. So let me do that. I'm sorry, solve for h of s. Right, so now I have all the y's on one side, the x's on the other. And I'm going to mark this because this equation is sort of a fork in the road. I'll use this two different ways to get to h of s or to get to the time domain thing. So I'm going to sort of put that with a red star. So the next step is if I want to find h of s, now I'm back to very familiar territory, right? I can factor the y and x out and then solve both sides. Okay, so I've got y and x factored out, and so then my next step is, remember, h is equal to y of s over h of s is equal to y of s over x of s. So when I sort of cross divide, so I divide both sides by x over s and 1 plus 2 over s, I'm left with y over x of s on the left-hand side, and minus 5 over s plus 3 divided by 2 over s plus 1 on the right-hand side. So there's my system function. If I wanted h of s, I wanted to go on from here. I might also, we like to see system functions in terms of positive powers of s. So we could multiply both numerator and denominator by s. So if I do that and then rearrange the order of the terms to put the s terms first, I get 3s minus 5 over s plus 2. So there's my h of s. If this is causal, that tells me the ROC will be bigger than minus 2, the real part of s greater than minus 2, because if I'm drawing a block diagram of something, it generally implies that it's a causal thing, because I'm going to build it in some sense. So I can assume from this my ROC is that the real part of s is greater than minus 2, because looking at this system, I have a pole of the denominator at minus 2, and for a causal system, I know the ROC goes to the right of the pole. Okay, so what if instead of finding h of s, I had asked you to find the differential equation? Well, you could unmultiply this here and get back up to something like the red star. We could just pick up from the red star. So let me scoot down the page. Right, so I'm going to start from this equation here to find the differential. So here's again where I need to exploit my knowledge of Laplace transforms. As I know these 1 over s type things are integrals, and I want a differential equation. I need derivatives. And so derivatives are things that have derivative in time are s's in Laplace. So I'm going to multiply both sides of this thing by s, because the biggest power in the denominator is just a first order s. So I'm going to multiply this through by s the whole way. And that should clear out all the integrals and turn them into derivatives. And now I go through just term by term, doing an inverse Laplace transform using my razor-sharp knowledge of Laplace properties. I'm exaggerating. There's really only 3 you need to know, right? Multiplying by s in Laplace is a derivative. So this is dy dt. Adding 2 Laplace transforms is still adding and scaling by a constant. So 2y of s, if I take the inverse Laplace transform, is 2y of t. Continuing in this way, I get my final differential equation here. dy dt plus 2y of t is minus 5x of t plus 3 dx dt. And so I can see that this is a first order differential equation. And if I scroll up, I can see how all these original pieces that were labeled in green, like these feed forward things, became coefficients on the derivative side, or on the input side. And the feedback thing, the feedback branch here, what this gained became the feedback of y of t. So again, we'll get practice as we start to do more of these. You see more clearly the patterns lining up where feed-forward branches turn into coefficients on the input, feedback branches turn into coefficients on the output. It takes a little time and practice to see how they line up, but I'm pointing this out now so you can start seeing these patterns and begin developing that practice with it. Okay, so that's all for this time. I'm going to stop here, and I will see you in the next videos.